Hello everyone, my name is Devshankar Mandal and today I will be discussing the hashing algorithm SHA-512 which stands for Secure Hash Algorithm. So it is a member of the different variants in the SHA family and is usually based on the Merkle schemes. Okay, so we will see how it is working. We can see that we can describe our hash algorithm in the generic term as small h, which is the output, the hash that is generated from the algorithm, which is equal to h. Capital H is the hashing algorithm that we are deploying to a message m. We have seen few requirements for this h. First thing it should be able to handle variable size input, but we should be able to produce a fixed size output. Thus, it should have to satisfy the one-way property, meaning given the output, which should be computationally invisible to find the input. Then it should be collision resistant. So these are the requirements that are necessary for designing a hash algorithm. In hash, we achieve the hashing techniques to achieve the security service of integrity. And hash is a one-way function. It is computationally infeasible to get back the message from the output hash. So SHA-512, it depends on the name standard is based on the output pitch that is generated. If the output that is generated on the small h is going to be 128 bits, it is known as SHA-1. The output that is being generated is going to be 256 bits, then it is SHA-256, and if the output is going to be 512 bits, it is known as SHA-512. So the output 512 is called as the hash code. So in this algorithm, capital H is the is algorithm, M is the variable size input that we are going to process, and 512 bits is the output. So these are the characteristics of the various variants in the SHA family. So we have SHA-1, SHA-2, 224, 226, 384, 512. 512 is the one which we are going to discuss. So these are the various characteristics against which we need to understand this algorithm. So what is the maximum input that it can process? It can process up to 2 to the power 128 minus 1. So this is the capability of 512, and the message that is received, it is split into blocks and it is processed as blocks. So the block size here is 1024 bits. So whatever the input, it is divided into chunks of 124 bits. It is processed one block at a time. The output that we are going to generate, the hash code, is also known as the message digest, which we discussed. So the message digest, the size is going to be 512. That is the output. That output is generated by this algorithm is known as the message digest. That size is going to be 512 bits. The number of rounds that is used here is 80 bits, and then we will use something known as words here. Char makes use of words. We will see what are words, and each word is going to be 64 bits. So for each round, totally there are 80 rounds. Each round will make use of a word. So there are totally 80 words, each of size 64 bits that will be generated. So these are the characteristics which we will be discussing. Each will be 64 bits, and each round will make each of a constant use of a constant which is expressed in hexadecimal, and those constants will be given to us, and the intermediate output and the final output will be stored in buffers. So the total size of the output is 512 bits, and the size of each buffer is going to be 64 bits. So totally we need 512 divided by 64, that is 8 buffers. So we will be making use of 8 buffers. So the purpose of these buffers is to store the intermediate results as well as the final output, which is the hash code. Each buffer will be 64 bits, and there are totally 8 buffers. So 8 into 64, which will give us the output of 512 bits. So SHA or any hashing algorithm will work based on the chaining process. So in chaining process, what we do, the output of the previous block is given as input to the next block, and in the last block we get the hash code. And usually the first block will not have any content, so we will fill it with an initialization with that. Okay, so we will see how we are going to fill the initialization with that. So this is the chaining process in sharp. Likewise, so we take a 5 with initial value, we process the first block, and we get the intermediate result. this intermediate result is given to the next block. So the compression function and the block it produces the next intermediate result, and so on we process, and we have processed the last block. So this is our entire message, and we have divided the message into chunks of 120 24 block, 1024 bits each block. So they are totally here, they are n blocks, and we are going to process that. Okay, we will see how we are going to process. So the very first step is given an input divided into blocks of 1024 bits, and how we are going to do the input processing. So the input processing is we have to know what is the original size of the message. Based on that we will do padding. Okay, so that we are able to fit the entire message, overall message, into a multiple of 1024 bits. Okay, so that is the first thing that we have to do. So first what we have to do is we have to first find the original plain text. Okay, the original message, its corresponding length. The final requirement is the original length should be less than 2 to the power 128. So as far as characteristics, okay, as far as characteristics, the original length should be less than 2 to the power 128. That is the first requirement. Then we take that original message, we express this length in a binary notation using 128 bits. This is the second step. The first step is we need to find the length of the original message. We ensure it is less than the processing capability of the shaft hypothetical algorithm. Second step, we express the length of the original message as in a binary notation, in a 128-bit notation. We do a padding to adjust the variable length so that this block becomes a multiple of 1024. If the entire size was say 3000 or something, the first block would be 1024, second block would be 2048. From 2048 till 3000, whatever was the remaining, we have to do the padding appropriately. How do we do the padding? We have to take one followed by multiple zeros. So this is how we will be doing it. So before we create the digest, we need the length field to be computed, which is the original input message length. So we express that in 128 bits. That is the length of the original message before pairing. Of that is the length of original message, it is 128 bits. Then we need to pad virtual message so that it becomes the length of 1024. So how much we should pad, that we have to do based on this formula. So that is this 128 is the length of the original message which we are expressing. This is the original message, and we need to pad something suitably so that this entire branch becomes a nice, which is a multiple of 1024, so that it satisfies the equation. So to find padding, we take the terms to the other side and we take a minus mod and we solve it. We'll just take a simple example. So here we take a simple example. Assume the original message is 2590 bits, and then we want to find what is the size of the pad. So here we usually have three components. So we have three components. So this last component will be 128 bits to denote the that it is the length of, and then here I have my original message. So 2590. Now I need to add something so that this entire branch is a multiple of 1024. So what we do is we take minus 2590 and minus 128 mod 1024. We add them, we get minus 2718 mod 1024, and after solving that we get 354. So the padding consists of 1, which should be followed by 353 zeros. So this is how we do the padding. Now this branch now has to split into blocks of 1024 bits. So we dive into corresponding blocks of 1024 bits. This is how we split it. So first step is input processing. And input processing, we take the message, we find its length, we express it in terms of 128 bit length. Then we subtract both and we find out how much we added to and how much should be padded. The padding is done followed by 1 followed by that many zeros. This is the entire branch. We then split into blocks so that we are able to process each block at a time. Now these are some questions which we commonly ask about the padding. Okay, so if the given input message, I'm going to process the message, the original message say it was 2048, which is actually a multiple of 1024. So now I should do the padding, yes, because the original message is 2040, but I need the receiver should know the length of the virtual message, whether there was an original padding or not. So we need to insert the length of the message. So we have introduced 128 bits again. So this makes the original message now go out of sync with the multiple of 1024. Then the second and third question is what should be the minimum number of bits that can be paired and what is the maximum number of bits that should be added. So suppose the original length of the last block, the original message say it was some number somewhat and the last block at 896. Okay, so the 896 bits means let's proceed. Okay, so we should be 896 minus 128 and we process it. Okay, so totally we need to add at least this many bits. So we need to do the padding as 0. Okay, so no padding means then the block should be at least 896 bits for maximum length. What we should do then, the maximum length should be, we should be able to pad at least 897 should be the maximum bit to complete. So now we are going to do the formal processing of the algorithm. Here SHA works on words. Each word is going to be 64 bits, meaning we will take one block at a time. One block is current, with the current block I'm processing is going to be 1024 bits. This block I'm going to split into 16 words. Each word is going to be 64 bits. Okay, so now what we're going to do with it, as we discussed here earlier, we said each round there are 80 rounds and each round is going to make use of a keyword which is going to be 64 bits. Now this is the point that we're going to discuss how we are going to generate 80 different words to be given as input to the 80 rounds and each word has to be 64 bits. So whatever is in the current block is 1024 bits that we are going to split and from the first 16 words because 1024 divided by 16 will be 16. Okay, so word 0 to word 15 will be obtained from the given current block. The current block is split into 64. The first chunk is going to be word 0, second chunk is going to be word 1 until that last chunk will be word 15, and we will still need two more words because totally we need 80 words, so we are going to generate the remaining words. For that we will follow an operation. So again, under the diagrammatic notation, the given block we are going to split into 16 words. Each word is going to be 64 bits. So this is my current block and I'm able to generate the 15 words as such. From the 16th word till the 79th word we are going to follow this process to generate the words. Based on that, we are going to make use of these words to generate the remaining words based on this formulation. Okay, so in this diagram, I'm going to explain from the given input sequence how we are going to generate the remaining words. So to generate a new word, what we are going to follow this formulation. Okay, it is going to be sigma 1 word the corresponding t minus 2 plus word p minus 7 plus sigma naught for t minus 15th index plus word t minus 16. Here the plus is going to denote addition modulo. Okay, that is the operation used here. So this sigma 0 is and what are the sigma 1 and what are the internal operations. So sigma 0 of a particular element is nothing but we are going to do a right rotate by 1 which plus right rotate by 8 bits, then we're going to do a shift left and which with padding by 0 on the right. So this is the sigma 0 and sigma 1. What we have to do is have to do a right rotate by 19 bits, then we have to do a right rotate by 16 bits, then we have to do a shift left by 6 bits with firing by zeros on the right. So in this way we will be able to generate the 16th word, then the next word and next one and so on. This is the way in which we are going to generate words to be given as input to the each round algorithm. Each round takes one word and the word is going to be 64 bits in size. The first 15 words will generate, the first 16 words will directly generate from the given message by splitting it into chunks of 64 bits. The remaining words, 16 words, 17 words, 18, we will following this notation. Okay, so this is how the simple example. If I want W60, then what 60 the formula is we have to substitute T here as 60. Okay, so it should be sigma 1 of W T minus 2, which will be this term comes first here, then formulation, then we are going to process here. Okay, same methodology, but we just process it. Now we will go on to understand the message digest. What is message? If it is the hash code or the output. The output means the outputs are usually stored in the buffer. We said right, the buffer is going to be 8 words each. Each buffer is going to be 64 bits. That is going to be 512 bits. That is 8 into 64, which will be the total size of the message digest, or the hash code will be 512 bits. We said in this training process, the initial round will not have any content, so we need to fill this buffer with the message digest with some initial values, with some initialization vector. So here in SHA-512 we make use of some constants for initialization, which is given like this. So we initialize the buffer. Now we can go on to understand the message digest. The message, if it is the hash code or the output. The output means the outputs are usually stored in the buffer. The buffer is going to be 8 words each. Buffer is going to be 64 bits, that is going to be 512 bits, that is 8 into 64 will be the total size of the message digest, or the hash code will be 512 bits. In this training process, the initial round will not have any content, so we need to fill this buffer with the message digest with some initial values, with some initialization vector. So here in SHA-512 we make use of some constants for initialization, which is given like this. So we initialize the buffers. The buffer is given as A B C D A F G H with some values from the hexadecimal given assets here. Okay, so these are the values that we are going to make use of for initializing the 8 buffers. We are going to do the processing of the algorithm. So this is the entire message. And this was the first step that we discussed. This was the entire message. We found the size, uh, and we expressed it in 128 bits. Then correspondingly we did the padding. This was step 1. So then we were able to formulate totally, and in 2024 with step of the total size, and we were able to get blocks of n. So we had m1 m2 till mn blocks. Each block was 1024. Now we are going to have initialize the message digest with the given hexadecimal values, which we are going to call as 80. This 80 and the first block m1 will be given to the will be given as input to the f function. Totally the function will have 80 rounds. Okay, so we will have 80 rounds, and after processing that will be given. Okay, so the current input is then processed here along with it to produce the next round output, and this step keeps on controlling until we generate the final hash code. So now we have seen how to split the message, how to do the padding, and how to do the length computation and for each 1024 bits. Then we have initialized the IV vector. Now we are going to see how we are going to process one block at a time. Processing of SHA by 12 bits one block at a time, and within one block that this function which is going to do 80 rounds, and that is known as the compression function. So this compression function usually takes 80 rounds, and each round takes 3 inputs. One is the keyword that we discussed, the other is the k constant, and the intermediate is here the plus indicates the addition module of 64. So round 1 block processing, 1 block of processing. So 1 block here denotes this part of the diagram. So here we are going to take this 1 block and we are going to give it to this f function, and we are going to see what is going to happen to produce output here. Okay, so this is the thing that is happening. This is the M, that is 1024 that we received. This is the 80, which is 8 buffers. Each power is going to be 64. Totally we have 512. Okay, so then there are 3 inputs we said. So from the message we will generate 80 words. The first word is given for the first row, the second word is given for the second row, and the nth word is given for the nth row, and the last word is given for the last row. And there are 80 constants which we denote as K0, Kp, K79, which is used. Okay, so and we are going to do, you will see what is happening in each row. So in this diagram, this is we take one block and we are going to process that one block to convert this H I minus 1 to H I. Okay, so we are going to convert this intermediate output to the next intermediate message digest output. So to do this process, this takes 3 inputs. One is the M, the other is the K, and the previous H. Not from the message, we are going to generate 80 words, and we need also 80 constants. Now we will see what is inside each round. Okay, so understood the same with a preview in a better way. We get the results of the previous block for the initial digest, and we are going to get the values for the next block. We are going to make use of words from the corresponding block and the constants. So what we are going to process after the 80th round, the previous thing is added here is using the addition modulo. This part here, okay, the previous round is added to this output using addition modulo, and that output only is going to form this round intermediate hash code or message digest that is generated. So this constant k not till k79 are given here. This is based on finding the cubic root of different prime numbers, and they are given here. So these are the values of the constants k0 till name is utilized in a SHA file for each of the 80 rounds. Now we'll see what happens inside each round. We are going to expand and zoom in on what is going to happen on each row. So in each round, what is going to happen? We are going to give. We are going to take this A B C D F G H from the previous block, and we are going to generate the A B C D V F G H from the next block, making use of W naught and K naught. Let's see what happens. So now a few contents are just given to the adjacent people. For example, A becomes the new B, B becomes the new C, C becomes the new D, and E becomes the new F, F becomes the new G, G becomes the new H. And A and E are something different. Here is some computation followed for finding the new A and the new E, which are going to denote as X and Y. Okay, so X and Y, this X what we compute using this logic will be the new A, this Y which we compute using this logic will be the new E. Okay, so what X computes is it is going to take 3 inputs ABC, ABC. Okay, so here this we're going to call it as majority. We'll go step by step on each block. Okay, majority is ABC, so here it is going to take the majority of the 3 bits that is given. If all of the 3 bits are 0, then we get 0. If all of the 3 bits are 1, it gets a 1. So at least 2 should be a same number to get the majority, but at least at 2 ones you get the output as 1. So there are 2 zeros, you get an output of 0. So majority should be at least 2 right out of 3. So you get that you take these 3 elements and you find bitwise between them, and you find the majority, and then you do a rotate here. Rotate is rotate by the corresponding bit. The bit portion will be specified, and you do addition modulo always here in this. Let's in the addition modulo to power 64, and this is called as mixture 1. This mixture 1 is again added to it this output to get the okay, here in this what they're going to do is they're going to take H E F G, and I'm going to take H E F G. What they're going to do is On EFG, they are going to do a conditional. What is the conditional? Is if it is going to be X, if E is going to be true, then it will return F. If E is going to be false, then it's going to return G. That is going to be conditional condition on X, Y, Z. If X then Y, then otherwise if it is not X, it's going to be return Z. Okay, then we are going to rotate it by E. Then we are going to do an addition modulo. Here they are also going to do addition modulo in these 5 terms. The H, this conditional operation, this rotation by E, the word generated for this round, and the constant that is used for this round, all these are done for an addition modulo that intimidates the output, is taken as mixture to output, make sure one output, and it is added to get the output for the new A. This output is again added with D to get the output for E. Okay, so this we will explain in the diagram, same stuff, but in a formal way. This is the diagram in the textbook, and this is a diagram which explains it better. So we are going to use this conditional function, majority function, to compute the next one. So only A and E are updated. The other elements are going to be the previous elements. And so what is the majority function? What is conditional function? What is rotate function? So in majority function, it is going to be, you have to find the majority between the 3 elements. Suppose they are this A, B, C. Suppose your C and your A were 1, and your A, B, and your C, assume those out of these 3. We need to find the majority. We will assume that A is 1, B is 0, and C is 1. We will check whether this returns 1. A and B will be 0. 0, B and C will be 0. C and A will be 1. So we will just do an x1, x0, or 0, 0x, or 1 is 1. So it returns the majority. Conditional will return, it is based on your E. If it's going to be true, it will give us F. If the C is not going to be true, then it is going to give us G. Okay, then there are 2 rotate operations which we saw. Rotate E, rotate A, and rotate key. Okay, and rotate E, how much you have to rotate, how much we are rotating. Okay, so here it is rotate right by 28 bits, and then rotate right by 34 bits, and then rotate right by 29 bits. Everything we are going to rotate corresponding, and we are going to take rotate right by 25 bits. We are going to rotate again, rotate E by 3, rotate it by right by 35. X we are going to take E, we are going to rotate by 29 bits. All those values are going to X, or and that's answer utilizing. So these are some simple